Hello and welcome to the latest instalment of the poster series brought to you by Edinburgh Instruments. I'm Angela and I'll be talking you through our poster today, focusing on multimodal microscopy characterization of 2D materials. So what will you learn from watching this video? I will discuss how we can use the RMS 1000 Raman microscope in a multimodal manner. We will look into determining the number of layers present in a tungsten diselenide crystal. Firstly, I'll discuss Raman, and using Raman imaging, we can look at a specific peak, both in its intensity and its position, to determine the number of layers present. We can then couple that information with photoluminescence imaging, where again, we look at the peak, position, its shape, and its intensity to determine exactly how many layers we have at each area of the crystal. And then finally, we bring in Second Harmonic Generation Imaging. And this gives us information about the symmetry of the stacking of the layers of the crystal that is present. So why do we care about tungsten diselenide? Well, it is an example of a 2D transition metal dichalcogenide monolayer material. As we move on, I will refer to these materials as TMDCS, as that is a lot easier to say. And these materials are an emerging class of thin layer crystals. They're of particular interest to researchers, progressing on from the beginning with graphene due to their unique optoelectronic properties. In bulk form, these materials have an indirect bandgap. However, when they are grown as monolayer crystals, they become direct bandgap semiconductors. And it's this property that has prompted the substantial research effort into the characteristics, specifically for optoelectronic devices such as photovoltaics, and solar cell research. So the layer thickness for this is very important, because the number of layers present is crucial for optimizing the materials for specific optoelectronic properties. So we need to identify layer thickness. What do we need from our instrument? It must be sensitive to the number of layers present. It must be non-destructive. We don't want to ruin our material just to find out how many layers are present. It must be fast. It must be rapid. We don't want to be waiting around for ages to determine how successful the growth method is for providing the number of layers we're aiming to get. And obviously it must be accurate with a high spatial resolution. How much information can one instrument measure? Can we have one that does it all? Well, I'm pleased to tell you, yes, we can have one instrument that does it all. Using our RMS 1000 multimodal confocal microscope, I'm going to demonstrate exactly how we achieve this. So first of all, for the Raman and photoluminescence measurements, we use an internal CW532 laser. To optimize this for Raman, we use a high groove density grating. So this means we're looking at a smaller spectral range with a higher spectral resolution. To optimize for photoluminescence, or PL for short, we use a low groove density grating. And this means that we see a wider area of spectral range, and this is needed to see the entire emission range from the photoluminescence spectrum. For second harmonic generation, we can use the external laser coupling port for the instrument using a pulsed 80 MHz 1040 nanometer laser. For all three of these techniques, we've used the same objective and CCD detector. And finally, what software does this all as well? So we use Ramical. This is the software that comes with our instruments. And this controls all the laser and scatter paths as we move from the 532 laser between gratings and as we use the SHG laser as well. We set up identical mapping areas and dimensions and parameters to make it easy to rerun mapping the same crystal with all three techniques. And once we've ran all the maps, the software was used to analyze the spectra. So the important parameters I mentioned before, the peak intensity, the peak position, and a feature called spectral matching was also used. Let's start with Raman spectroscopy. So Raman imaging is a very normal place to start when we're looking at materials such as graphene or these 2D TMDCs. For tungsten diselenide, we get a very characteristic peak at 250 wave numbers, and this corresponds to the in-plane E12G and out-of-plane A1G phonon modes. What's interesting here is that both of these contribute to the one peak. For other crystals of this material type, we normally get a peak for each individual phonon mode, whereas here we get one peak of both combined. The intensity of this peak is directly correlated to the number of layers present. So areas that are monolayer in nature provide a higher Raman signal. The peak position itself also provides information on the layers present. The peak is redshifted, i.e. it moves to areas of a higher wave number. As the crystal no longer is monolayer, when it becomes multilayer, we see this redshifting. We also see significant edge effects with peak position, and this is due to the extremes at these microenvironments where they're being grown, and it includes factors such as stress and strain. Another interesting spectral feature of the tungsten diselenide is the emergence of an additional peak at 310 wave numbers. This peak is actually symmetry forbidden in monolayer crystal, and therefore it is another indication that we have multi-layered tungsten diselenide present. So using Ramaco's spectral matching, we can summarize there are three distinctive Raman spectral regions. We have monolayer tungsten diselenide, which is highlighted in the blue color in figure C. And then we have the inner area, which can be determined to be multilayer due to its emergence of peak at 310 wave numbers, which is labeled in the spectra on the right-hand side of the image. However, it's showing us two areas of multilayer tungsten diselenide due to a slight difference in peak shape. Now, from the Raman spectra alone, we can't really determine exactly what's going on with our crystal here. Thankfully, we can now move on to another imaging technique to find out more. So let's move on to photoluminescence or PL imaging. So another interesting feature of tungsten diselenide is that its Raman spectra doesn't offer that significant layer information, especially in comparison to other materials of this class. So for example, molybdenum disulfide, the Raman spectra is really distinctive between different layer numbers, but this is because it produces those two individual Raman peaks from the two separate phonon modes. Because we don't have this for tungsten diselenide, we must use another technique to probe the sample more. And photoluminescence imaging is a great technique to gain this information. And again, we don't even need to change our laser for this. All we need to do is move to a different grating so we see our full spectral range. Starting with the intensity of this peak, we again see areas high in signal can be labelled as monolayer. We can then plot in peak position, and we see the peak is redshifted on areas of multilayer tungsten diselenide. Where we see a lot more information is from spectral matching. So this time we've identified 4 regions. I'll start with region D, purely because this is the edge effects again. So it's not really what we're interested in, but what's interesting specifically from the photoluminescence data is we actually see that the edge effects have 2 different edge effects. We see this because, or we know this because, in some cases the photoluminescence is blue shifted, and in other cases it's red shifted. And this is information we didn't gain from the Raman spectra. Moving on to the areas that do interest us, we see in blue again our monolayer tungsten diselenide. Now this has a photoluminescence peak at 780 nanometers, and it corresponds to 1.6 electron volts. The emission from bulk, which is indirect bandgap tungsten diselenide, occurs at 1.2 electron volts, or 1000 nanometers. So we can use this information to figure out from our peaks of this crystal what is going on in that central area that we know from the Raman is multilayer. So region B, which is shown in red, shows a decreased photoluminescence intensity, and we start to see the appearance of a shoulder in its spectrum at 870 nanometers. So that's moving towards the 1000 nanometer peak if we were looking at bulk tungsten diselenide. So from its position, we can determine that this is going to be bilayer tungsten diselenide. And when we move to region C, the intensity of the photoluminescence has decreased again. And now, when you look at the spectra, it doesn't really have a defined peak at 780. This shoulder at 870 nanometers is becoming more the dominant component of the spectra. So this means we can assign this as tri-layer tungsten diselenide. So this is really interesting. We started with our Raman spectra, our Raman imaging, where we knew we had some mono and some multi-layer tungsten diselenide, but it wasn't quite enough to really have a look at these areas. So by using photoluminescence imaging, we can now really narrow down exactly how many layers are present in each area of the crystal. But what if we want more information about the crystal and how those layers are actually stacked on top of each other? Well, now we'll use Second Harmonic Generation Imaging. This was used to probe, as I've mentioned, the symmetry of the sample. The technique requires a very high excitation intensity, which is achieved by using mode-locked femtosecond pulse lasers. As I described before, this is extremely easy to do with the RMS 1000 thanks to its external laser port. The phenomenon of SHG only occurs when there is a non-central symmetry in the excitation focal volume. Monolayer tungsten diselenide will always meet this category and therefore will always have a significant SHG response. For multi-layered tungsten diselenide, the symmetry depends on the type of layer stacking present, of which there are two, 3R or 2H. In 3R stacking, each layer has the same orientation, making the multi-layer non-central symmetric, and the SHG response will increase with increasing layer number. In 2H stacking, each layer is rotated 180 degrees with respect to adjacent layers. This means in odd-numbered multi-layers, these are net non-central symmetric, providing an SHG response similar to monolayer tungsten diselenide, and for even-numbered multi-layers, they are net central symmetric, meaning there's absolutely no SHG response. Using this information, coupled with the Raman and photoluminescence data we've already taken, we can now assign the multi-layer regions to specific stacking symmetry. So the bilayer region has an SHG response double the monolayer. So logically, this must be 3R stacked. Region C, the tri-layer, has diminished SHG response. However, it still has some second harmonic generation. So this means that the third layer is rotated relative to the first two layers. So there is a partial restoration of central symmetry, which explains the decrease in SHG response. So let's quickly recap what we found out from today's poster. Well, firstly, I demonstrated how using Raman imaging reveals areas of the crystal that are monolayer and areas that are multilayer. Specifically, that the center of the crystal had an area that was multi-layer tungsten diselenide. However, it was quite vague in the information there. So we progressed to photoluminescence imaging, which provided complementary information and even higher detail, meaning we can now assign areas of the center crystal to be bilayer and areas to be trilayer. Second harmonic generation was then used to look at these two areas of multi-layer tungsten diselenide to find out the stacking orientation. And overall, we demonstrated how the RMS 1000 can be used in a multimodal way. Multiple characterization techniques were used on this crystal tungsten diselenide for rapid analysis, but also really highly detailed analysis for layer determination in TMDC crystals. And that brings us to the end of the poster presentation. I focused on tungsten diselenide, and below is the link to the full application note. If you give this a read, you'll find out a wee bit more about the data I presented today. And you will also be linked through to other areas of research on graphene and molybdenum disulfide, for example. If you have any questions about the RMS 1000 and how we can optimize it for your research needs specifically, please get in touch. So thanks for listening to this poster presentation on characterizing 2D materials by Edinburgh Instruments.